on Synopsys Spyglass technology and provides a comprehensive set of early RTL testability analysis capabilities. It includes all the features found in the legacy Spyglass DFT ADV product, and it can be run on an RTL or gate-level design. Testmax Advisor is commonly used throughout the design implementation flow at various handoff points when the design's content changes. The advantage of running Testmax Advisor at different checkpoints is that Spyglass design constraints, or the SG-DC file, is common throughout the flow. Now let's talk about the key features and capabilities of Testmax Advisor. Testmax Advisor can be used to check a design for DFT violations, and this provides an early insight into the testability problems. This speeds up time to DFT and ensures that RTL is scan-ready. Apart from DFT violation checks, Testmax Advisor also provides the maximum achievable ATPG coverage estimate for the design and also reports the hierarchical coverage estimate for the subblocks and hierarchies. This helps to determine whether the coverage goal can be achieved and which blocks or hierarchies are contributing to coverage loss for the entire design. The random resistant fault analysis feature in Testmax Advisor can be used to analyze the hard-to-test faults in the design, which can impact the ATPG efficiency in terms of pattern count and runtime, and provides an ordered list of test points which can be inserted to reduce the pattern count, thereby lowering the test cost. The connectivity checks in Testmax Advisor help to validate the DFT and structural connections at system-on-chip assembly. As mentioned earlier, one of the important features of Testmax Advisor is ATPG coverage estimation. Please note that Testmax Advisor provides consistent and repeatable correlation between RTL and ATPG test coverage. For StuckAt, Testmax Advisor's coverage estimate correlates within 1% to the actual ATPG coverage, whereas for transition delay, Testmax Advisor's coverage estimate correlates within 5% to the actual ATPG coverage. These correlations are expected provided that the DFT constraints are aligned between Testmax Advisor and ATPG. In this section, we will talk about the Testmax Advisor. This is an overview of Testmax Advisor flow, showing the input files needed to start the Testmax Advisor run, the needed setup files to control the run. Testmax Advisor can be invoked in the same ways as legacy Spyglass DFT ADV product. These are the different ways to invoke Testmax Advisor. Like, this invokes Testmax Advisor GUI in interactive mode with the settings specified in the .prj file. When you load a project file in Testmax Advisor, the stage at which you last closed the session gets loaded with all the saved data. This invokes Testmax Advisor in GUI mode with the settings specified in the .prj file and runs the specified goal. This invokes Testmax Advisor in batch mode with the settings specified in the .prj file and runs the specified goals. Now, Let's take a quick tour of what the TestMax Advisor GUI offers. The Analyze Results window is active after the goal run is complete. This window can be used to view the results of that run and access debug capabilities. This shows the module or instance tree for the design and lists all the hierarchies. This can be used to select whether the messages are displayed by rules or severity. This shows the session log and captures the progress of run. This can be used to specify criteria for search in the message window. This is the interface for waivers. This provides the help for selected messages. Double-clicking message highlights related RTL source code. This provides links to debug utilities. This is the search window. TestMax Advisor parses a Verilog of VHDL, RTL or netlist design and creates a flattened view of the design so that DFT checking can be done. A logic simulation engine is used to apply and propagate the constraints in the design. This full-blown cycle-based simulator is integrated inside the tool along with the other engines like the parser and the logic synthesis engine. A built-in set of rules called guideware is also provided to the user for references. Now let's talk about the project file, which is the main file that controls the TestMax Advisor run, including reading the design and constraints, selecting a methodology and goal, and customizing the goal by using options and parameters. It includes 3 sections. The design import section to read the design, libraries, and the STDC file. The common options section to set the global options for all goals and also the parameters. And the goal setup section to select a methodology, specify a particular goal, and adding or removing rule checks. This is an example showing the design import section in a typical project file. In the design import section, read file is used to read in individual RTL or netlist files, the STDC files, and the libraries. Read file -type HDL can be used to read in the RTL or gate level design. Read file -type source list can be used to read a source list which includes the list of design source files. Read file -type gateslib can be used to read in the libraries, either .libs or sglibs, which are the Spyglass compiled version of .libs. Read file -type STDC can be used to read in the design constraints included in an STDC file. In the common options section, the options needed to control the flow need to be set, like set option top specifies the current design you want to run TestMax Advisor on. Set option DWES is used to map the designware components. Set option enable SV enables system Verilog support. Set option allow module override allows only the last found module or UDP definition to be processed, and earlier definitions with the same name are ignored. By default, duplicate module definitions result in syntax error. Now let's talk about the methodology setup section in a project file. Guideware is the built-in reference flow and methodology in TestMax Advisor. It helps to prioritize testability checks in terms of which rules to run first. It includes 3 methodologies: initial RTL, RTL handoff, and netlist handoff. And these methodologies include various goals. These goals include predefined set of rules and parameters which can be configured as desired. The initial RTL methodology should be used when RTL is still in coding development and may not be functionally complete. The RTL handoff, which is the default methodology, is a superset of initial RTL goals. It includes the complete set of recommended RTL handoff checks. Netlist handoff methodology is designed to check post-synthesis netlist prior to layout. The desired methodology can be set using current methodology as shown here. After setting the appropriate methodology, appropriate goal needs to be selected in the project file. These are the most important goals used for DFT analysis in TestMax Advisor. The DFT Scan Ready goal analyzes scan readiness of the design, reports the maximum achievable STUCAT coverage by ATPG, and also provides a step-by-step approach to maximize the coverage. The DFT Best Practice goal checks the design for best coding practices to maximize ATPG coverage and efficiency. DFT DSM Random Resistance goal analyzes the design for hard-to-test faults which could impact ATPG efficiency and writes out an ordered list of test points. These test points can be inserted into the design to reduce ATPG pattern count. DFT DSM Best Practice goal analyzes the transition coverage of the design and provides a step-by-step approach to maximize the coverage. The goals in TestMax Advisor are sequenced, so it does not make sense to run test point analysis to increase fault coverage until the design is DFT Scan Ready clean. The desired goal can be set in the project file using current goal as shown here. Parameters in a project file can be used to control the analysis by rules and the reports. They can be set in the project file using set parameter as shown here. It is recommended to set the parameters under current goal specification. To report default values of parameters under current goal scope, write report goal setup or get parameter dash default can be used. These are some of the examples of using parameters. This example shows the goal setup section of a project file. You will need to select a goal as appropriate for the design analysis using current goal after selecting the current methodology. Set goal option may be used to add or ignore rules after specifying the current goal. Any goal-specific parameter should be set after setting current goal so that it remains in context of the goal. We talked about the project file in TestMax Advisor in last few slides, and now we are going to talk about SDDC file, which includes the design constraints for DFT analysis in TestMax Advisor. The SDDC file needs to be read in through the project file using readfile-type SDDC. The Spyglass design constraints file includes all constraints needed to configure the design in test mode, like clocks, resets, test modes, or constant signals. Sanity checks are performed on the SDDC files for existence of design objects specified in commands and also if a mandatory field for a command is missing. The TestMax Advisor run aborts on these errors. We will go through the constraints which are used to specify clocks, resets, and other signals in our SDDC file in the coming slides. Test clocks for the design are specified using clock constraint in the SDDC file. Dash test clock option with clock constraint specifies that the clock will be used for scan shifting as well as for STUCAT capture. Testmax Advisor allows applying the constraints like test clock, test modes on internal nets. This facilitates performing test analysis on early stage RTL when the design is not frozen and test structures have not been inserted. In actual situation, both test clocks and test modes must ultimately be driven by the ATE and hence have to be defined on the top-level ports. This will be the case when the chip RTL will be finalized. Test mode constraint is used by Testmax Advisor to simulate constant value on respective node in the design. This constraint can be specified for different phases of test operation. For example, -scanshift option indicates that this constant value needs to hold during shift phase only. Similarly, -capture option applies the constraint during capture phase only. The intention of applying this constraint is to configure the design for test mode of operation. It is expected that all the test requirements should be satisfied with the help of application of this constraint. The asynchronous sets and resets in the design are also specified using test mode constraint by specifying their inactive state with -value. Please note the usage of -scanshift here, as the DFT requirement is that the asynchronous resets and sets should be held inactive during scan shifting only. If test mode is sequential, then you have to apply a sequence of values on the respective nodes. All the test mode constraints are simulated by the simulator in parallel. One way to handle essential black boxes is to apply a scanwrap constraint on them. This constraint lets Testmax Advisor assume that there is a scan ring around the module. Hence, it is able to consider the fan-out cone of logic to be controllable and the input cone of logic to be observable. This constraint can only be specified in black boxes. You will have to black box a synthesizable module by using set option stop in case you need to apply a scanwrap constraint on it. The parameter DFT set all BB scanwrapped can be set to make all the black boxes to be considered scanwrapped. This may often turn out to be a handy tip for the designer working with early stage RTL. You may wish to exclude a few instances in the design from being scan stitched. For example, the clock or reset generators or the BIST logic, etc. This intention is expressed through the force node scan constraint in Testmax Advisor. These instances are not checked for clock or reset controllability as part of the scannability checks. The controllability or observability analysis automatically gets adjusted to take care of such non-scannable flops or instances. Till now, we talked about Testmax Advisor and its important features. We looked into the Testmax Advisor flow setup, the project file, the SGDC file, and various constraints needed to configure the design. Now let's talk about these features in detail, the DFT violation checks, and the ATPG coverage estimation in the next section. Now let's look into the key testability goals. In this section, we are going to focus on DFT Scan Ready and DFT Best Practice goals in Testmax Advisor, which can be used to perform early testability analysis in terms of scan readiness and coverage analysis for a design. Let's look at some important user interfaces and reports which are offered by Testmax Advisor for early testability and coverage analysis. The schematic viewer can be used to debug the violations reported by most of the rules. The fault browser is helpful in analyzing the test coverage issues in a design as it categorizes all hierarchies in terms of their contribution to total coverage loss. The StuckAt Testability Impact Report or Coverage Audit Report reports the current estimate of maximum achievable StuckAt coverage by ATPG and also provides a step-by-step approach to increase the coverage. Similar report is available for transition delay. We will talk about these interfaces in detail in the coming slides. By auditing a design for test coverage, one can get an early estimate of coverage under the constraints provided to Testmax Advisor. The recommended goal to run at this stage is DFT Scan Ready. The DFT Scan Ready goal generates a report, the StuckAt Coverage Audit Report, that reports the current estimated coverage and guides the designer to take step-by-step approach to increase the coverage, as we will see in the coming slides. This is an example StuckAt Coverage Audit Report displayed in the Testmax Advisor GUI. The Coverage Audit Report profiles the design to show reasons for ATPG test coverage loss because of incomplete test intent for the 3 ATPG modes, the shift, StuckAt capture and at speed capture, and the topology or structures in the design that make false ATPG untestable. The StuckAt Coverage Audit Report gives you a prioritized list of issues that have the biggest impact on the test coverage loss. That is, the scannability DRC is at the top of the report. The last couple of categories in the report can only be addressed with the insertion of test points to increase the number of faults that are ATPG testable. The most important value of this report is that test points are used as a last resort to increase coverage. Since this analysis can be run on RTL prior to code freeze, many testability issues that impact optimal ATPG coverage and ATPG efficiency can be identified early on. This has a big impact on the last-minute ECOs to address testability. The report indicates the current coverage for the design and the steps in tabular format that you need to follow to improve the coverage. For each step, there is a description of the root cause, the improved fault and test coverage number if the reported issues for the step are fixed, and the diagnostic rules to debug the respective steps. For example, in this report, the test coverage can be increased from 94.2 to 97.5 by applying ScanWrap on black boxes and reviewing the test mode constraints. As we discussed earlier, DFT Scan Ready is the recommended goal to analyze the design for scan readiness. In this example, the StuckAt Coverage Audit Report indicates that the coverage of design can be increased from 70.5 to 97.9 by making flip-flops scannable. And for that, violations reported by Clock 11 and Async 07 rules need to be looked into. The DFT Scan Ready goal includes these two main rules, Clock 11 and Async 07. The Async 07 checks that asynchronous sets or resets driving the flops should be inactive during shift, and the Clock 11 rule checks that clocks driving the flops are controlled by test clocks during shift mode. The flops which pass these two rules are treated as scannable by Testmax Advisor. This example shows how to debug violations like reported by Async 07 rule. Async 07 is an error, and that is why it is shown in red color. The symbols mean that there is a spreadsheet and an incremental schematic available for debug. You may browse through violations and use the schematic viewer to debug the violations. First, you will need to select the violation, right-click on it, and select Incremental Schematic to open the schematic viewer. This displays the Async07 violation in the schematic viewer. The violation shows that the reset of flop on the right is at X and is not set inactive during shift. Please note the various annotations used by schematic viewer on the nodes to display the values. Like for example, sh_1 denotes that particular node is fixed to a constant value 1 in the shift mode, whereas sh_caret means that there is a clock propagating through that node or a clock constraint on that node. DFT Scan Ready goal runs the info coverage rule to report an estimate of stuck at test and fault coverage. Report of coverage per module is also generated so that user can focus on the worst offending module. To generate a detailed ATPG-like report with fault type status, the parameter DFT generate stuck at fault report needs to be set to all. The hierarchical depth of coverage report can be controlled using the DFT coverage report depth parameter. Even a target coverage can be set using DFT target stuck at fault coverage parameter, and a warning is issued if the estimated coverage is lower than that. Now let's see how you can invoke the fault browser in Testmax Advisor. To open the fault browser, you will need to select the message reported by info coverage rule and then click on DFT tab in the GUI. This shows a sample fault browser invoked from info coverage rule run as part of DFT Scan Ready goal. Test and fault coverages can be browsed per hierarchies, and the hierarchy causing maximum coverage loss can be noted from the test coverage loss column. It is possible to dive further deep into the hierarchies for coverage analysis. The design details are reported as part of the info DFT debug data rule, which is run as part of DFT Scan Ready goal. The info DFT debug data rule reports the design characteristics in terms of the number of flops, the number of latches, the number of clock getting cells, the number of memories. Each of these sections has spreadsheet in terms of CSV file associated with it. It is possible to click into each of them to get the details about individual elements. DFT best practice is the recommended goal to check for good design practices in order to maximize ATPG coverage and efficiency. This goal includes rules like Tri-State 06, Clock 04, Topology 01, etc. Some of these rules are now going to be discussed in the following slides. Tri-State 06 rule checks for tri-state bus contention, which can be a critical factor for good design as well as for DFT. It can be very important for BEST. Often the designer knows that in normal operation, the state circuit prevents bus contention. The problem arises in scan or BIST mode when arbitrary states can occur that may produce contention. This rule checks the tri-state enables on all buses to ensure that no combinational values can cause contention or bus float. Generally, such a rule requires formal verification approach, but we have built-in means to check this rule in Testmax Advisor. Topology 01 rule checks that the combinational loops in the design must be disabled. A combinational feedback is a problem because it can cause ATPG tools to produce unreliable tests and can result in lower fault coverage. In this example, a combinational loop is created. The rule Topology 01 helps identify such loops. One solution is to allow such feedback so long as the loops are disabled or forced to known states by test mode. As you see, The addition of test mode input to the OR gate forces a constant value at its output and thereby disables the loop. Clock 04 rule checks that the clock signals in the design are not being used as data. This is an example where the clock used for test purpose is also used to feed data to the flops. The ATPG tools often cannot work with such situations. This is detected by the Clock 04 rule, which is included as part of the DFT best practice goal. Latch 08 rule checks for latch transparency in the design. The ATPG tools can efficiently process the combinational circuits. However, the latches in combinational logic must become transparent during capture mode in order to capture the system response to the scan flops. During this mode, such latches should be reduced to buffers. If the net driving the latch enable pin can be controlled to its active value, then there is no issue. In this case, the ATPG tool can generate a vector to make this latch transparent. On the other hand, if the same net cannot be controlled to the active value, then latch 08 shows up as a warning message. In this case, the designer needs to modify the design in a similar way to the way shown to ensure that the latch becomes transparent. In the last section, we talked about the DFT violation checks and ATPG coverage estimation feature in TestMax Advisor. In the next section, we will discuss the random resistant fault analysis and test points feature in TestMax Advisor. In this section, as we discussed earlier, DFT DSM random resistance goal needs to be run to perform random resistant fault analysis on a design. This goal analyzes the design for hard-to-test faults, which could impact ATPG efficiency, and writes out an ordered list of test points, which can be inserted to reduce ATPG pattern count. Random resistant fault analysis, that is RRF analysis in TestMax Advisor, is performed on faults that are ATPG testable but are hard to test, that is hard to control to 0 or control to 1 and hard to observe. These hard to test faults have high impact on ATPG efficiency in terms of runtime and pattern count. While RRF analysis focuses on stuck-at faults, the biggest impact on pattern count reduction is for transition delay fault testing. This analysis ranks all ATPG testable faults by creating a metric based on the probability of control and probability of observe, thus identifying the faults that are hardest to test. Once the hardest to test faults are identified, TestMax Advisor writes out an ordered list of test point locations to improve controllability and observability, thus improving ATPG efficiency. Random resistant fault analysis feature in TestMax Advisor runs info random resistance rule to estimate the random pattern detection profile of a design. This rule estimates design's random pattern coverage by calculating the probability of controllability and observability for each node, the stuck-at 0 and stuck-at 1 fault detection probability, and the average of all the fault detection probabilities. Examples of structures which can lead to hard-to-test faults are wide and deep logic cones, complex combinatorial logic, for example, cascaded XOR gates found in comparator logic, the IPs which are most likely to have the above logic are the comparators, ALUs, memory-based controllers, or logic-based controllers. This is how info-random resistance rule generates an ordered list of test points for a design to increase the ATPG efficiency. It calculates the probability of control and observe for each eligible node. Then it selects design nodes based on sensitivity to random resistance of the design, followed by estimating the impact of each test point on each such design node. Based on this, it suggests a test point on the design node where estimated improvement is highest. Then, it virtually inserts test point in the design and adjusts the probabilities of detection score, and then finds the next best test point in the design. To summarize, the incremental improvement in random pattern coverage reported for a test point in the list is based on the assumption that the previous test points in the list have already been inserted in the design. These are the important parameters to control RRF analysis in TestMax Advisor. DFT pattern count can be set to any positive non-zero integer to specify the number of test patterns considered for coverage estimation by the info-random resistance rule. By default, it is set to 8000. DFT RRF TP count can be set to any positive number or percentage to specify the required number of test points to be suggested. By default, this is set to 5% of the total flops in the design. DFT RRF TP generate DC report can be set to generate random pattern DC test points report, which can be read by DC or DFT Max for test point insertion. By default, this is on. DFT RRF TP cutoff incremental gain can be set to any decimal number between 1 to 100 to specify the minimum desired gain as a percentage for a test point to be considered for the design. By default, it is set to 0. DFT RRF TP effort level can be used to specify the effort level for finding test points. By default, it is set to medium and can be set to low or high. Setting it to high can lead to runtime penalty. As we discussed earlier, DFT DSM random resistance goal can be used to run random resistant fault analysis on a design. This shows an example from running DFT DSM random resistance goal. Info random resistance rule is run as part of this goal and reports the random pattern coverage and test points for the design. After random resistant fault analysis is run, fault browser can be opened from info random resistance rule. You will need to select the message under info random resistance rule, right-click on it and select fault browser option. The fault browser helps to analyze the distribution of hard-to-test faults for different hierarchies in the design. The hierarchy contributing to the maximum loss in random pattern coverage for the design can be noted from this report, and it is also possible to dive deeper into the hierarchies. It is possible to analyze the hard-to-test faults in design using the thermal map available with random resistant fault analysis feature. To analyze, you need to select the message under info random resistance rule, which reads these many faults with lowest probability. Right-click on it and select incremental schematic to open the thermal map. This is how the thermal map window looks like. It shows the different hierarchies with hard-to-test faults in the left window. Any hierarchy can be selected and double-clicked to get the relevant faults in the schematic on right window. The probabilities for control, observe, and detection are displayed for every node in the schematic, which help in the analysis. The parameter DFT-RRF-TP generate DC report controls the generation of test points file for DC or DFT max, and it is set to on by default. To open this report in GUI, you need to click on Reports tab and go into More DFT Reports and select Unified Test Points Report. The test points file reports the type, location, and corresponding incremental gain in random pattern coverage for every test point. The No Test Point constraint can be used to exclude modules or instances which should not be considered for suggesting test points. The fan-in logic or fan-out logic options can be used to exclude the unblocked fan-in or fan-out logic also, respectively. Apart from RRF test points, TestMax Advisor also provides other types of test points. The TA_10 rule reports test points for improving controllability or observability of nodes in a design. Like for example, this net is uncontrollable because it is being driven by a non-scan flop. Inserting a control test point will enable the tester to control this node to the desired value during scan. This is an observable net, and inserting an observed test point will help to increase observability. Now let's talk about the physically aware test point insertion flow using TestMax Advisor and TestMax DFT. We all know that increasing the number of test points typically decreases test pattern count, increases test coverage, or both. But it also impacts timing and area. The physically aware test points insertion flow provides the ability to easily add physically aware test points to minimize their impact on timing and area. TestMax Advisor is run under the hood, and it selects the test points by analyzing which nodes need to be controlled or observed to improve ATPG efficiency. TestMax DFT inserts those test points along with the other DFT logic, and Design Compiler Graphical optimizes the design in terms of timing, power, area, and condition. It utilizes both placement-based and timing-based methods to minimize the test point's impact on timing and area. The flow is simple and requires minimal effort from the designer to achieve great results. The inserted test point registers are shared with multiple test point locations based on physical and logical proximity of the locations, which helps to reduce area. By default, maximum of 8 locations are shared per test point register, and this is something which can be configured. As all the optimizations are based on physical data, it helps to reduce congestion and does incremental optimization for timing. The end result is reduced pattern count and/or increased coverage with no timing and low area overhead. Now let's see how to enable the new physically aware test point insertion flow. The test points are inserted during Insert DFT in TestMax DFT and can be enabled using Set DFT configuration -testability enable. Set testability configuration can be used to configure the test point insertion, like selecting various targets. For example, random resistant target is for random resistant fault test points. Untestable logic target is for TA_10 test points. Multiple targets can be enabled in the same run, but should be configured separately. The number of test points to be inserted can be controlled. Run test point analysis is used to run TestMax Advisor after pre-DFT DRC, and set testability configuration -sg command file can be used to pass specific options to TestMax Advisor from TestMax DFT. In the last section, we talked about random resistant fault analysis and test points feature in Testmax Advisor. We will look into connectivity validation in the next section. In this section, with growing complexity of system on chips, design for testability is getting more and more challenging in terms of targeting complex fault models, achieving low DPPM and high coverage. As design sizes grow in complexity, the challenge to validate that auto-inserted test logic infrastructure has been implemented correctly is getting more difficult. Ad hoc methods like visual inspection, scripting, test benches for exercising test modes, and other methods are very time consuming, particularly debugging the root cause when there is an issue. And the root cause of majority of issues at system on chip level, including simulation failures, is incorrect connectivity or improper setup control. And that is why the users need to detect and fix the DFT connectivity issues early in the design flow to make sure that there are no connectivity verification escapes causing ECOs close to tape out. This describes the typical DFT connectivity verification challenges faced on system-on-chip assembly. Top-level IPs like PLLs, sensors, BIST controllers, fuse, and monitors are manually inserted. The generation and optimization of JTAG and hookup with test IP and test logic is manual. The design change frequency is high, and all these connections need to be verified at every stage in the ASIC flow. Some users have to do manual top-level integration of blocks that have complex compressed cores and manually added pipeline flops at top level. To reduce debug turnaround time during ATPG DRC checks, running a quick check to verify pipeline depths, connections, and external chains could save time. Now let's see what are the advantages of using connectivity checks. Testmax Advisor Connectivity Check feature provides a robust and accurate solution to perform these connectivity checks using very compact and readable constraints. It helps to identify the root cause for failures effectively and easily, minimizing the false violations and noise effectively. Regressions are supported with this feature so that the connectivity checks can be quickly performed with any ECO flow to validate that DFT connections are intact. The constraints used with connectivity checks can be made technology and design independent so that they can be reused. Let's see how the connectivity checks can be run. The connectivity checks need the CON rules to be run as appropriate. Testmax Advisor has a predefined goal, DFT test connections, which can be used to run the connectivity check CON rules. Or a custom goal can be defined using define goal to include the connectivity check rules. This is a quick breakdown of some important checks that can be done with the CON rules. Like expected state of a design node can be checked using require value constraint, which runs the CON01 rule. Require path constraint can be used to check for existence of a path between specified nodes, and it runs the CON02 rule. The illegal path constraint can be used to check that a path does not exist between specified nodes, and it runs the CON09 rule. As we discussed earlier, the STDC file includes the design constraints needed for analysis in Testmax Advisor. In order to perform connectivity checks, SGDC file needs to be modified to include connectivity-specific constraints apart from clock and test mode constraints. In this example, please note the usage of require value, illegal path, require path constraints to perform the specific connectivity checks. We discussed earlier that the connectivity checks in TestMax Advisor can be made compact and technology and design independent. Let's see how this can be done. TestMax Advisor connectivity intent takes a collection of design objects via predefined logical names or macros. For example, specific pins of flops, latches, muxes, clock gating cells, etc. These macros make specification compact, readable, and flexible, especially when hierarchical paths are unknown. These macros enable you to define logical names for a collection of generic design objects, such as flip-flops, latches, and muxes, for which you want to perform a particular check through a set of SDDC commands. For example, flip-flop data signifies all D-pin flip-flops in the current design. CGC test enable signifies all test enable pins of clock gating cells in the current design. Memory clock signifies clock pins of all memories in the current design. Each connectivity constraint makes reference to one of the built-in modes or a user-defined mode in TestMax Advisor. These are the various built-in modes in TestMax Advisor connectivity checks. The power ground mode simulates and propagates all the tie-offs in the design. The scan shift mode applies all scan shift test clocks and test mode constraints scoped for scan shifting. The capture mode applies all capture mode test clocks and test mode constraints scoped for stuck at capture. Capture at speed mode applies all at speed capture test clocks and test mode constraints scoped for at speed capture. Now let's look at some typical examples for require value checks in a design, like a check to validate that the PLL resets in the design are not active, or a check to validate that the test enable pins of clock gating cells are not tied low. These scenarios can be validated using require value constraint. This example shows the usage of require value constraint to check that all PLL resets are inactive. A user-defined mode tag PLL reset inactive has been defined using define tag to specify the condition that the top-level primary port PLL reset N is held at value 1. And then require value constraint is checking for all PLL resets to be at value 1 in the specified mode using require value -tag. As you can see, con01 rule is being run for require value constraint in TestMax Advisor. Here, con01 reports a violation for a PLL's reset pin, saying that it has active value 0 instead of required 1 value. The violation can be analyzed and debugged using the incremental schematic. This example shows the usage of illegal value constraint to check that test enable pins of clock gating cells are not tied to 1 or 0. Please note the usage of macro CGC test enable to specify the test enable pins of all clock gating cells in the design. Con10 rule is run for illegal value constraint in TestMax Advisor, and here con10 reports a violation saying that test enable pin of a clock gating cell has illegal value 0. This violation can be analyzed and debugged using the incremental schematic. Now let's look at some examples illustrating the point-to-point connectivity checks. Like a check to validate the TDI port is connected to D input of bypass register in the bypass mode, or a check to validate that all the core clocks to IP are being driven by outputs of clock gating cells. All these types of scenarios can be validated using require path constraint in Testmax Advisor connectivity checks. The require path constraint can be used to validate one-to-one connection, one-to-many, and many-to-many connections. One-to-one connections like node A is being driven by node B. One-to-many connections like inverse of tap ATPG shift signal drives the shift end pins of all memories. Many-to-many connections like JTAG data registers drive the MEM SVS pins of memories. This example shows how require path constraint can be used to validate that all the flip-flops except in a particular hierarchy, subsystem 3U0, are receiving clock from one of the clock gating cells in the design. And this is an example of validating many-to-many connections in the design. Please note the usage of two macros, the CGC clock out to include all the clock gating cells outputs, and flip-flop clock to include all flops clock pins. The violations or existing paths can be analyzed using the incremental schematic in Testmax Advisor. With this, we come to the end of this Jumpstart training. You should now be able to list the key features of Testmax Advisor, that is the DFT violation checks, ATPG coverage estimation, test point selection, and connectivity validation. You should be able to set up and run Testmax Advisor to generate the important reports and results, and you should also be able to interpret those important reports and results.